everyone, and welcome back to StudyOnion, and today we're going to be talking about Kepler's laws of planetary motion. Let's get started! So first thing we need to review is what is perigee and what is apogee. Perigee is the closest distance between the Moon and the Earth in its orbit around the Earth, standing at 363,300 kilometers, and apogee is the furthest away distance from the Earth in the Moon's orbit, and that stands at 405,500 kilometers. And let's have a quick review of the parts of the ellipse. The ellipse can be split into 4 parts. The longer axis is called the major axis, and the smaller axis is called the minor axis. The semi-major axis is halfway through the major axis, and you can see this labelled on the diagram on the slide. And so the focus point is the point halfway through the semi-major axis. With all that's being said, let's have a quick look at Kepler's first law, which is relatively simple. Each planet's orbit around the Sun is an ellipse. The centre of the Sun is always located at one focus of the ellipse. The planet follows the ellipse in its orbit, which means that the distance between a planet and the Sun is constantly changing as the planet goes around its orbit, and this is where we get our aphelion and perihelion, or your apogee and perigee. It's essentially the same concept. So let's have a little look at Kepler's second law, which is slightly more complicated. So Kepler's second law states that a line joining a planet and the Sun sweeps out equal areas during equal intervals of time. This means that a planet will be travelling fastest when it is at its closest to the Sun, which is also known as perihelion, and it will be travelling slowest when it's furthest away from the Sun, or aphelion. And we can see in this diagram what that means. It means that the same area is covered in the same intervals of time. And this would be the diagram that you would need to draw if they had asked you a question explaining Kepler's second law. So Kepler's third law is again slightly more complicated, and this one is more a formula or a proportionality equation. So what it is that t squared is proportional to r cubed. Now I'm going to illustrate something very carefully. T is the orbital period of the body, and r is not the radius of the distance to the Sun, but the mean distance to the Sun. It is not the radius of the ellipse. So what you can write this as is t squared divided by r cubed is equal to a constant, which in proportionality is typically symbolised by the letter K. And we can see that this holds true for all the planets in our solar system, where t divided by r gives you a value, and then if you do that for t squared divided by r cubed, you get the same value of 1.0 arbitrary units, and we don't give units for this because it is arbitrary. Now, you can use Kepler's law in application for different things. And what you can use this for is that time periods and mean orbit radii are related to the mass of the central body because of gravitation. Now this might look a little bit complicated, but basically all that they are saying is that the time something takes to orbit and the mean distance from which it orbits are all directly linked because of gravity. And that's all that this is trying to say. Now, this is a force between all bodies that have mass. Gravity is a force between every body that has mass, including me and usually we use these equations applied on the celestial level. So here this equation is saying that the constant of the orbital period divided by the radius of the orbit divided by another constant of the same proportion is equal to the mass of the first body divided by the mass of the second body, because they are inversely proportional. Okay, so let's have a little look at a practice question. Now, before we start, I'm going to make clear that these values are not realistic and are just values that are completely made up. So do not learn these numbers as figures, learn the numbers that I've mentioned to learn as figures. Alright, so I will just give you a couple seconds to work through this question and then press play if you want to hear the solution. Okay, so t squared divided by r cubed is a constant, which is k, and that is going to be equal to the orbital period squared divided by the mean distance. And the careful thing about this is that you have to be careful. R is not the mean radius, it is the mean distance. And that is equal to 12 squared divided by 5AU plus 1AU. And the reason I'm saying plus 1AU here is because the question has said Jupiter is 5.2 AU from Earth. So we already know that the Earth to Sun distance is 1 AU. So you have to add on your 1 AU on top of your 5.2 AU in order to get the mean distance between Jupiter and the Sun rather than the distance between Jupiter and the Earth. You then just do your calculation, and that will result in a constant value here that is 0.604209325, and that is equal to the k, or the constant, for this solar system. All you then need to do is substitute Saturn's values into t squared divided by r cubed on top of that, and you will have your answer. So t squared divided by 9.5 cubed equals your constant, so t squared equals 9.5 cubed times your constant, and that is equivalent to 518.03397, or to calculate that in t years, that is equivalent to 22.76035962 years, or rounding to 2 decimal places, 22.76 years. So, to summarise, Kepler's first law of motion states that the planets move in orbits around the Sun with the Sun at one focus. The points in the orbit which the planet is closest to and furthest away from the Sun are called perihelion and aphelion respectively. Kepler's second law states that the imaginary line from a Sun to a point on the orbit sweeps out equal areas in equal intervals of the time. In the diagram, swept out areas A1 and A2 will be equal. And finally, Kepler's third law is that t squared, which is the orbital period, is divided by r cubed, which is the mean distance from the Sun or any other star in its solar system, is equal to a constant. The only thing that will change in different orbiting systems will be the constant, and it can be shown that k inversely depends on the mass of the body. Hopefully that's helped you learn more about Kepler's laws and gravitation. I'll see you next time to talk about Newton, but for now, bye!